This video is on kinetic molecular theory and root mean squared velocity. So kinetic molecular theory has 5 different parts. It states that gases consist of particles. The volume of the individual particles is negligible because that volume of the individual particles is so small compared to the distance between them. Particles are in constant motion, so collisions with the container will exert pressure. So important here that collisions of gas molecules result in the pressure that we can measure. Particles are assumed to exist no forces on each other, so we say that their collisions are elastic. So it's like a rubber band, you can stretch it and it goes back just as it always was. Doesn't matter what you do to it, it's going to return back to normal. So particles assume no force on each other. And then average kinetic energy of particles is directly proportional to the Kelvin temperature. So this is where we get the information that temperature is a measurement of kinetic energy. Now, using physics equations, you can derive that, but essentially, the equation for kinetic energy is equal to 1/2 mass times the average velocity squared. Okay, this is for one particle, but in a gas we have many particles, so we're going to multiply that times Avogadro's number, which is a mole of particles. So kinetic energy is equal to 1/2 mass times average velocity squared times Avogadro's number, which gives us an average kinetic energy for a mole of particles, so for a gas. When we look at these variables, v squared is our average velocity squared, and m for this instance is mass in kilograms. So that's something we haven't used much. We usually use grams, so it's important to note that this mass is in kilograms. You can also look up and find that the pressure times the volume divided by moles is equal to 2/3 times the kinetic energy. When we set these equal to one another, we find that kinetic energy is equal to 3/2 R, which is our gas law constant, times temperature. Now, because we're using kinetic energy here, and energy is measured in joules, we need to figure out a new gas law constant with the units of joules per mole Kelvin. You can look this up. In fact, there's a chart with many different gas law constants. And depending upon your units, that changes the gas law constant you need. But for these cases, our gas law constant with joules per mole Kelvin is going to be 8.3145. So from this, we can see that as our temperature increases, this is a constant, this is a constant. So just help us make our proportionality. As temperature increases, so does kinetic energy. So as I have an increase in kinetic energy, my temperature increases. So temperature is a direct measurement of my energy, and temperature is in Kelvin. So it's very difficult to find the energy and velocity of a single particle. It's basically impossible. So because of that, we use averages, which is why we also talked about a mole's worth of particles, and we look at average velocity squared, and up here we talk about the average kinetic energy. So averages are what we're going to use. We can calculate something called the root mean squared velocity. This is the average velocity of the particles, and it has a variable, this fancy U, RMS for root mean squared, and its units are meters per second because it's a velocity. So to derive this equation, we have, again, our kinetic energy is equal to Avogadro's number times 1/2 mass times average velocity squared. Remember, because we're looking at the average, so we want a mole of particles. And we know that kinetic energy is equal to 3/2 RT. Setting these equal to each other and solving for average velocity of particles, we get 3 RT over Avogadro's number of particles times the mass in kilograms. This, multiplied together, mass times mole, is a molar mass, or the molecular weight, in kilograms. So here we're going to change this to a new variable called capital M sub W for my molar mass or molecular weight in kilograms. Solving this further, by subbing this in, I have my average velocity squared is equal to 3RT over my new variable M sub W. And then because this is squared and I want it unsquared, so my little u, my unsquared, from just my average velocity of particles, not my average squared velocity, I take the square root, and so my average velocity of particles, or my root mean squared, so root mean for average, so my root average square velocity, or root mean squared, is equal to the square root of 3RT over MW, where MW is my molecular weight in kilograms. So that's my formula listed here. Put a box around it. So in this case, again, R is my 8.3145 joules per mole Kelvin. It's a new gas law constant because there are new units. We're dealing with joules from deriving our energy or kinetic energy equation here. And M sub W is my molecular weight in kilograms. Okay. So if we do an example, we want to calculate the root mean squared velocity of helium at 25 degrees Celsius. So the great thing about this equation is the only things that are going to change are temperature and the molecular weight, and that's based on whichever gas we have. So all we need is temperature and molecular weight. Our temperature of 25 degrees Celsius, we need to put into Kelvin, so that's 298 Kelvin. And then my molecular weight for helium is 4 grams per mole. But I need to get that in kilograms per mole. And so I know that there's 1,000 kilograms in a gram. So that is 0.004 kilograms, or we could write 4 times 10 to the negative 3 kilograms. Either way is fine. So I plug that in to my equation. Root mean squared is equal to the square root of 3 times my gas law constant times temperature divided by my molecular weight in kilograms. So 3 times 8.3145 times 298 divided by my 0.004. I get 1.36 times 10 to the third, and my units on here, because it is a velocity, is meters per second. So that means that on average, my helium particles are moving 1.36 times 10 to the third, which is 1,360 meters per second. That's very fast, which we would expect because they're gas particles. So we can summarize that as temperature increases, my root mean squared velocity also increases. And we can look at our formula as my mass increases, because on the bottom, or on the denominator, my root mean squared decreases. So this means that heavy particles move slower.